Hello everyone. I'm Akhil, like Charlie introduced. Thanks, Charlie. Uh, and I'm a senior site reliability engineer at LinkedIn. And I'm going to talk to you about how we do our server fleet management, specifically for my team, which is a prototype, hopefully, to be used by the entire company in the future. So in the interest of time, let's get straight into it. I'm going to do a bit of the introduction of mine and then the company, followed by building context. And by that, I mean, before I describe the problem, it's important to understand the context, which tells us why it was important for us to kind of solve the problem. So I'll do that by talking about scale. Then I talk about my team, which is Espresso. And I hope you've had some coffee after lunch, because otherwise I'll be expecting some yawns. That said, I'll talk about then the problem set, which involves hardware, failures of hardware, and how we managed to work around them in a hands-off manner, which was an extremely time-consuming task for SREs in the past. And for those of you who don't know what SRE means, it's just a different term for DevOps. I'm sure you're aware of what DevOps is. Then I'll speak about what were the challenges that we had when we wanted to automate the whole cycle, and how Camunda fits the bill. And then I'll build, towards the end, upon the entire solution set that we have built with Camunda's help, and followed by what we look forward to in the future within the company and with Camunda. All right. So, like I mentioned, I've been with the company for over 5 years, and has been a great experience so far. I've been with different teams, but entirely within the data stack. So earlier with the NoSQL key value store, in between with the MySQL team, and then finally with the NoSQL document store. Over the last couple of years, I've had the good privilege of trying to build an automation platform within the team using Camunda, and that's what I've been working on integrating. All right, so LinkedIn, I think like Charlie mentioned again, most of you know what the company is about, but I'd like to quickly mention that it's more than just a jobs portal. The vision of the company is to provide economic opportunity for every member of the global workforce, and the way it does this is by creating an economic graph over the entire world by having entities like members, companies, jobs, skills and whatnot, and having relationships between all of these entities, which are called edges. And we leverage the knowledge that we gain from such a graph and then provide value to all customers and members alike. Now, what's important is the kind of scale that LinkedIn serves, right? And two important numbers on the website, on the screen that I want you to focus on is the number of members that we have. It's over 645 million members. So that's one. And if you look at it, that we have more than 2 signups a second, which is kind of what the scale of the platform looks like, right? And when we talk about the platform scale, it is built on technology entirely, and the technology scale looks something like this. And again, only a few numbers that I want to pay attention to is the amount of queries per second that we get to our edge, which is like the endpoint of where you talk to LinkedIn. And that's about 340,000. And take a look at 2 other numbers, which is the number of servers that we need to serve this entire traffic, which is over 200,000. And then ultimately the amount of data that we need to serve the online traffic, and only the online traffic, which is over 2 petabytes. Of course, there's a bunch of other data that we use for analytics and all of the other purposes, but this is the data in the online document store. OK, so this was kind of important to build context around why the problem that I'm going to be describing in the future will be important to solve, because it's the scale. If the problem was limited to like a very small website with a very limited number of users, then it may not have been as significant. So let's talk about my team, Espresso. We are essentially about 25 engineers, and we have created a NoSQL document store for LinkedIn. And it's kind of the combination of a relational data storage and a NoSQL key value store. It bridges the gap between the two of them. Importantly, the kind of use cases that we serve for LinkedIn are identity, the profile that whenever you log into LinkedIn, the profile that you see or other people's profiles that you visit is hosted on Espresso. And even things like in-mails and your invitations, which drive growth for LinkedIn, are also hosted. The data is hosted on Espresso. Quickly going not very deep into the technical side of what the product is, but just to give, again, a little bit of the context of the problem itself, is that it's basically every use case is a database on Espresso. Every database is sharded into multiple partitions, as you might be aware. Each partition has 3 replicas, and the servers that we have host at most 1 replica per partition and multiples of those partitions on it. And that's as much as you would need to understand about the product for the rest of this presentation. And don't worry if you miss some of the details in here, because you will still get the context regardless. All right, so what's the usage of Espresso like? So the 200,000 servers that I mentioned earlier, 16,000 of those host just this. About 85% of LinkedIn's data is also hosted on the service, so it's quite critical to functioning of LinkedIn entirely. And we have over 300 use cases and about 130 plus clusters. All of that makes the problem special and makes it worth solving for us. And part of what this talk will be alluding to as well is the fact that, I mean, a lot of people have been talking about and have in the past talked about at this conference of the business process automation. But I'm going to talk about some technical automation that we've been wanting to do using Camunda at LinkedIn. So that's kind of also what this alludes to. Now, of course, the software runs on a bunch of hardware, and one of the critical things about the hardware is the SSDs. SSDs are fast, basically silicon chips that help you store data. And what we do with SSDs is just store the data that's needed for the online traffic. There's a bunch of other data on the servers, like logs and stuff, that go to the not as expensive hard disks. But most of the online data is stored on SSDs. And I mention SSDs for a very specific reason, and the next slide will kind of tell you. But we have other hardware that's on the servers as well, like the motherboards, the memory, the spinning disks as well. Now, there's one thing that comes as a gift, as an unwanted gift with hardware, and that's failures. Essentially, all hardware is bound to fail, and it's bound to fail several times over its entire lifetime. And what, as a good software developer, we all need to do is make sure that they don't impact the functionality of the website in a way that's degrading, but essentially it gracefully degrades and continues to perform its function in a smooth manner. All right, so that said, what's the impact of hardware failures to Espresso servers, right? Let's say an SSD goes bad, it starts working slowly, latencies talking to the SSD spikes. What happens? So requests coming into the database become slow, sometimes time out, sometimes throw errors. So essentially results in an availability dip from the service's point of view. We talk about these numbers, 4 nines, 5 nines, 99.99% availability, and we take this very seriously. That said, the service has built-in capability to detect that in some time and then move on to start shutting itself down, and then that sort of resolves the problem for the time being, but at the cost of reduced redundancy. So like I mentioned earlier, all the servers host some number of partitions, and with this happening, the number of servers go down, the replica count goes down for the time being as well. And yes, there is spacing between lines over there, and that's very intentional, because the first 3 kind of mention what's the immediate aftermath of a failure, and the remaining 3 are what happen, things that happen some hours down the line, let's say 10 or 12 hours down the line. So if the server hasn't recovered in about 10 to 12 hours, what happens is the cluster manager that manages all the data across all the nodes reshuffles the data in order to make sure that all 3 partitions are available again, all 3 replicas of the partition are available again, and essentially that's taken care of automatically as well. But the result of all this automation is 2 critical points that are mentioned at the end of the slide are that now the capacity of the other nodes to serve traffic, the responsibility increases, and the disk utilization on these other nodes also increase. So if we were to allow this to happen over and over again, let's say 5 or 6 servers out of a cluster of, let's say 30, 36 were to go down, it will come to a point where the remaining clusters will not be able to take the deal anymore. And so essentially what we need to come up with is a way of tracking all these failures, making sure that the servers that go out of rotation are brought back into the cluster, and make sure that the serving capacity of the cluster remains as high as possible at all times. So that is essentially what the problem that we were looking at, and that is what we wanted to solve. again, it becomes kind of important to also realize what the frequency of these failures were, because one or two happening here or there may not have been that big a deal, and they could have been solved in a manual manner. But what we saw was, on an average, we saw 30 failures of such kind in a month, which is about one failure a day. And if someone were to manually look at these things and sort of do fixes in and out, it would become mundane, and that would not be the best use of an engineer's time at all. So hence the automation. Why we kind of needed it is all of this. Essentially, there were long cycles in which the hardware would get fixed, right? Sometimes SSD vendors would take even up to a month to provide the real root cause of what the problem with the disks are and how to fix them and how to bring them back in rotation. So that was one. The people that were doing the actual hardware fixes were, of course, not part of our team. They were data center technicians that worked at the data center, and they used Jira for most of the tracking. And essentially, what that results in is there is no automatic discovery when something is repaired. For example, a data center technician goes in and fixes the actual drive. It would be hard for us to get to know that because there is no automated mechanism of getting to know that. And lastly, the process, if it's manual, it's bound to have people missing steps. And when people miss steps, it would result in outages of various kinds because you brought in an unhealthy drive or a drive without preparation into the cluster. And that would just result in upstream clients getting lots and lots of errors. So hence the need to automate. If we sort of automate all of these things individually, we would get a system where there would be less time consumed in fixing the problem, less chances of failures in case of steps missing and such. So what did we need for automation, right? At a high level, we needed to automate two things. One, when there is a problem detected, you take the server out of rotation. When the problem is fixed. Second, when the problem is fixed, you bring the server back in rotation. As part of that, what we also needed to do, like I mentioned, was the automatic detection of the closing of Jira tickets, which is something crucial because otherwise a human needs to keep monitoring those and then trigger other processes. So this also needed to be automated, and which was crucial. The other bits were verification. This is more to do with the software rather than the automation itself, but we needed to make sure that it was safe to bring a node out, safe to bring a node back in, and to make sure that the correct version of software and configurations were deployed to the server as well. And if you look at all of that, it says there are lots of async waits essentially involved. So when you're waiting for a ticket to get closed, when you are trying to figure out what the right version of the software is, when you're trying to fetch that version and compile. So all of these were asynchronous waits, and asynchronous because you don't necessarily want your process to be synchronously waiting for some of these long-running tasks because they could last to a scale of 10 minutes or plus as well. So these are the kind of things that were requirements for our automation. And in essence, these 4 boxes describe kind of the 4 things that I'm talking about. You needed signals, you needed state. State because long-running signals from various systems because you did not want humans to sort of go and keep monitoring something. Essentially, we needed to write custom code to do the bits of figuring out what the software version is, and because that's very specific to the company, we needed to write custom code. And we needed some software that would asynchronously wait for something while the threads were being utilized for doing other processing, rather than just waiting on an external process to finish for over 10 minutes as well. And if these are the 4 things that you come across as needs for your automation, I guess what we found was Camunda was definitely our answer. And we evaluated some of the other automation engines out there as well, but this seemed like a feature fit set for our needs. So the solution essentially was a 2-part process. Like I mentioned, 2 high-level tasks, one to bring the server out of rotation and one to bring the server back into rotation once the problem is fixed. Now, we were going to use this new product called Camunda, and we were a team of engineers that were focused on doing databases right. So essentially, this was not going to be something we did as a primary task. And hence, there were entry barriers. The first, and this is kind of sort of new for all of you because most of you who do Camunda are used to writing Java and whatnot. But SREs at LinkedIn had Python as their primary coding language, essentially. And at the time, when we were trying to figure out what is a good way of integrating Camunda with Python, it didn't seem the most convenient. Although today, thankfully, I've learned a lot about external task framework and how we can leverage that to involve multiple languages. But at the time, this was one of our concerns. And we had to kind of migrate all the libraries that were written in Python into Java in order to support some of the functions that we really wanted. Because a lot of what I've been talking about is within the realm of SREs, and we do all the server management and all of that automatically as well. The other sort of entry barrier was integrating all of this within LinkedIn's deployment frameworks. For example, we build our software using Gradle. We deploy them behind Jetty servers. So the UI at the time, which was Tomcat friendly, was something that also was an entry barrier. Another point alluding to authentication, and I guess someone was talking about security earlier. We needed to make sure that our corporate authentication works with this, and we have two-factor auths as well, and so integrating all of that would also take some time. So what we decided was we would start small, and once we had the results, it would be easy to convince the management to put more resources into doing Camunda and providing a better scale solution for people across the company. So we picked up automation of part 2. And what that looked like, and like the 4 boxes I had drawn, one of them was signals. We had to do some preparatory work as well, which was basically getting the signals into Camunda. And in Camunda context, they are called messages. So we wrote a couple of message handlers. One for Kafka, because LinkedIn wrote Kafka as well, so it heavily uses Kafka for a lot of its functionality. And every event that fires anywhere within the infrastructure fires an event into Kafka. So it would be very, very useful to write a message handler so that anybody or any team could then start using Camunda as well. The other one, and also a significant one, was writing a Jira message handler, which would then track all the Jira events and then do things based on modification of ticket state, for example, the ticket being closed and whatnot. Apart from that, we had to do preparatory steps on the nodes as well, for which we leveraged Salt, and thankfully Salt had a REST API, and we could call onto REST APIs using Camunda as well. So we used that, and then some of the other stuff that I spoke to you about earlier. And this is what kind of the initial design looked like. It was a process that would wake up every day, figure out every node that was out of rotation, and because, like I mentioned, part 2 is only to bring in nodes that are out of rotation back into the cluster. It would go and look at the list of all the nodes that are out of rotation. In the box over there, which says hardware failure detection, it would confirm that there is a Jira ticket that exists, which confirms that there is a hardware problem. And then from then on, it would move and do things like go into a loop of checking whether Jira is closed or not. If closed, then bring the server back in rotation. Otherwise, do nothing. And this was the initial proposed design by me. But my colleague at the time, who was also investing in Camunda, kind of came to me and said that one of the better approaches of using Camunda within LinkedIn would be to make it a reactive system. Essentially, this would be something it proactively did every day when it woke up, rather than an event-based system where if we detected that there was a ticket that's getting closed or whatever, then we fire an event, and that event kind of creates a workflow instance, rather than a workflow instance being created every day where we don't know whether there is an action to take or not. So this became the final design, where if you see the 2 message handlers that I mentioned earlier are being utilized in the first 2 message boxes. One would receive a message from Kafka when the node went offline. The other would receive a message from Jira when the ticket was operated on, either closed or not, that's secondary, but every operation on the ticket would be tracked. And then again, the same loop of figuring out when the ticket gets closed and performing all the steps to bring the server back in rotation. In essence, this makes it look very useful, but this problem was difficult to solve without Camunda, because we'd had to write all of these going from one state to another, like in a programming language. We would have to write the timer tasks, and all of that would just become very complicated to do entirely on our own. So this became very, very useful. We did a couple of other things as well. What we needed was notifications coming out of the system. If you realize this system tempers with production hardware, and anything that tempers with production needs to give out notification to the responsible teams. So what we did was we built into the history event handler, and we plugged into that. Also, we use something called a composite DB history event handler, which takes all the default functionality, and then you can add on top. So we added on top, and what we did was any event of the type process instance end would sort of generate a success message or a success notification to the on-call. And in case of an instance create, which is generated whenever an exception happens, it would generate another kind of alert to the on-call saying, okay, something failed and you might want to go and look at it. So doing this kind of solved the high-level problem for us, but like every software, there were glitches, and there were glitches that thankfully were resolvable. And I'd like to point some of them out because if there is anyone that will look at this presentation in the future as well, I guess this can help them sort of, work around some of the initial problems that one could face. So one thing we noticed was that some of our jobs, and I use jobs in a very Camunda context where between two transaction boundaries, let's say there are 2 or 3 tasks, it becomes like a job. And we saw retries of these multiples of tasks happening even when the underlying task would succeed. And it took some time to figure it out, but there is a default job lock timeout within Camunda's process engine that's set to a value which is less than what what the underlying process was taking. So we figured that out. We updated it in the process engine before deploying the process engine at deploy time, and that helped us solve that problem. One caveat about that is that if you change that, it would apply to all of your, basically all of your jobs within the workflow. And so if you needed like a short timeout, then this would not work for that. Another thing we noticed was that there were notifications being sent out incorrectly, as in repeatedly as well. And this notification was being generated by the event handler that I mentioned earlier. So on digging a little bit deeper, we found out that the enum that is initializing the history event types was doing something incorrectly, wherein the name and the type were both being initialized to the name itself. And that was a bug that was fixed and then made available with a later version of Camunda, but we had already patched it. And at this point, while writing the presentation, I also thought that because it's an open source product, I could have applied the patch myself. But the next bug will be a patch on my name as well. There were a couple more. And the first one was where we called into the REST API sometimes to do a part of the workflow. Whenever, let's say, for example, the Jira ticket closed, but the workflow failed with an exception, we would need to trigger a message manually to make it look like the Jira ticket was closed. And those messages, when sent to the REST API, were resulting in a class not found exception. And thanks to Generali's presentation here, I think a couple of years ago, just by Googling it and figuring out the YouTube link, I could figure out that the problem was that our job executor was not deployment aware, and that I was using asynchronous executions not in the most correct way. So that got fixed. And then essentially the last one, and I'll skip over that very quickly because of restrictions about time, is that I made an assumption that Camunda enforces business key uniqueness. In essence, if there were multiple workflows were instantiated with the same business key, my assumption was that it would fail and it would take care of it internally, but that's not the case. So we wrote some amount of code within our message handlers to make sure that we can drop the duplicates. With all of this, we were still stuck with that original thing where we mentioned that we would solve a small problem, get results out of it, and then that's what we'd use to convince the management of investing more resources into this. So we needed metrics. So because we had the event handler written already, what I did was generated a metric event from within the event handlers without blissfully realizing that Camunda provides some of the metrics by default. Although that said, we needed more real-time metrics, so we did some more research, and although I haven't implemented this yet, I looked at something called a Prometheus plugin to the process engine, which does this real-time metrics. And I heard in today's talk earlier that all of these are being provided by the Camunda Optimize, yes, the Optimize framework as well. All right, so we were successful, as expected, and we saved about a month of SRE time within the first 2 quarters itself. And like with all business process management, I think the focus was on optimizing in some way to save money. Essentially, this costs a lot of money to LinkedIn as well. A month of any engineer's time is a lot of money, so we did end up saving a bunch of money. That gave us enough metrics to go forward with the other part of the workflow that I was talking about. And this diagram isn't as important now because things had changed by that time. We needed to do more than what we had promised earlier. So instead of it being a two-step process, and I know I'm rushing a little bit, again, just due to the time. But instead of it being a two-part process, now we needed to do something else. And let me talk about that a little bit. So if you notice during the two workflows where you take a server down and then you bring a server in, there's a large gap in between that I was kind of alluding to, where the underlying problem is being fixed by an external party. And if that can go on for months, like I mentioned, that results still in the server, in like reduced capacity of the cluster. And I mentioned earlier that one of our aims was that we keep the capacity up at all times. So naturally, what we wanted to do was anytime we saw a failure, we would, yes, bring the server out of rotation, but instantly swap in a new server for the old one. And sort of building onto part one of the previous design would help us do the same thing within Camunda itself, because we had some REST APIs available to do swapping of instances. So it became a new design where there were three parts: take the server out, swap the server, and bring. So what changed is now when the problem was fixed with the old server, instead of coming into a live cluster, it would go into a spare pool from where we would use instances for swaps. So that became this. Essentially, this is part one, where you take the node out of rotation. And if you notice carefully that the first part after the message is received is checking for throttling conditions. Why this was necessary is if, let's say, the upstream system, which was sending signals to Camunda to say that there is a problem with the server, were to go haywire or there was a bug, the automation would result in taking the entire fleet down if, for example, that message was being generated for every server in production. So we needed to be careful about that, and security was very, very strict about this, that we could only do a few instances per day. So we wrote throttling into the workflow itself. Now, it's interesting to talk about this as well, because doing it within the workflow and within the instance of the workflow didn't solve our purpose. Essentially, what we ended up then doing was writing this into the message handler, which would instantiate these instances. And because the message handler has access to process engine and everything that's going on with the MySQL instance of Camunda itself, it could figure out the number of instances that had run at the time or during the day or any of that, and we leverage that to make sure that we don't run more than X instances per day, we don't run more than X instances per cluster, and whatnot. So that was one of the interesting bits that we did, and I wanted to mention that it's better to write those things outside into a message handler that spawns the workflow rather than trying to do that within the workflow. And why is something I'll mention in a while. Part two was swapping the node, like I mentioned. Now, we did not want reduced capacity in the cluster, so swapping the node was simple as finding a candidate from the spare pool. If you found a candidate from the spare pool, you would start swapping the instances, wait for the swap to succeed enough to call it a success, wherein it would start taking live partitions and start serving traffic, and then call it a day by sending out a notification to the on-call that I have done something in production, and you don't need to worry about this problem at all. Part three is something we got for free. The first design that I mentioned earlier, which was the first thing that we did with Camunda, was bringing servers back in rotation. We just changed one task in the original workflow definition to make it such that instead of bringing it into the cluster, it would put it in the spare pool. So essentially, this three-part problem, and I'd like to take a minute to just talk about that. This three-part problem helps us do a lot, not just within the context of our team, but also outside the team. It starts with detecting a problem with the server. And this happens to most of the technology companies that run on their own data centers, and LinkedIn does that too. A lot of the times, data center technicians need to wait for an engineer to give them a go-ahead that, OK, I'm going to do some tampering with the host because there is a problem that I have detected. And that causes frustration for them, that causes frustration for the receiving team, that, OK, why am I having to do this day in and day out as a part of my job? So this three-part problem helped us automate all of that. A data center technician does not have to wait for somebody's approval. What will happen is, as soon as the fault is generated, the server will be kicked out of rotation, will be put in a repair pool, auto-approve the maintenances that the data center technician needs to make in order to get rid of the fault on the server. And so essentially, this removed most of the human communication from the entire picture itself, and people could do their jobs just relying on some signal that came out of Camunda. And yes, this helped us solve the capacity problem as well, where there would not be less than one. So essentially, let's say it was a 10-node cluster, there would never be less than 9 nodes in the cluster, because as soon as the problem was detected, we would swap it out, and for that duration, maybe we would be 1 minus the total strength, but otherwise we would be at the entire strength of the cluster at all times. There were a couple of minor challenges, and throttling, like I mentioned, was one of them. And the reason why I mentioned of doing it outside the workflow rather than trying to do it inside was this one, that if, let's say, lots of messages were coming in parallel to your process engine, what it would do is spawn all of these instances, because you were doing the check inside the workflow to basically identify whether we should throttle or not. And if all of these came in parallel, your workflow would not be smart enough to do that, because at that point, you've already spawned the instances. And then dropping the workflow instance or calling it quits at that point was not the most elegant solution. So we did it outside. We did it with a lock in place. So our synchronization was also not a problem. The other one, I think I'll skip over in favor of questions from the audience, because I think I'm running over 30 minutes already. But quickly mentioning just what our deployment looks like. We have a MySQL instance owned by the MySQL team at LinkedIn, which is an advantage of being like a giant company. We don't have to worry about it. All the upgrades of latest MySQL and all of them are done by the team itself. The UI is built using Gradle and hosted behind a Jetty server, but we haven't faced any issues with that, and I know it's supported in the industry now. We have each workflow or all of our different use cases deployed as a separate application within the company, and one of the things that we want to change is that with a one-click deploy or whatever we've been hearing about today, what I want to do is make sure that I'm hosting just one application, and any user that wants to create a new workflow definition can just go and deploy it to that live instance rather than managing their own service. And essentially, I think what Charlie mentioned in her introduction as well is what we've built is a service called Perseus, which takes Camunda as a dependency, writes a lot of LinkedIn integration libraries, because we are doing a lot of modifications using the internal libraries, and then packages it into this in this nice product called Perseus. And that's kind of what our deployment looks like. There are other use cases that we've hosted, but I guess you guys can look at this when I share the slides with you and also on YouTube. But this is what the future of Perseus as a service now, which involves Camunda at the core of it. And I guess a lot of microservice discussions that happen here are also related to this, is I want to build a platform for automation within the company. It's not about us, our integrations with external clients or whatnot, or all of that, but a platform for everyone in the company to be able to do something like a Camunda playground, where they create all these diagrams, just write, OK, this task is to be done by this executor or this helper or whatnot, and then just go ahead and deploy and see how that works in production, because this will be crucial to its success. One of the other things I'm looking forward to is implementing metrics in a better way, that we want real-time metrics, and I'm going to start looking at what all these solutions that are provided by Camunda and the Prometheus engine as well that is available in the open source are going to help us, and how they're going to help us. And the last one is the cluster setup. But again, Camunda Cloud kind of covers that ground, and I'm going to investigate more into figuring out how a cluster setup looks like, where we can share workloads between different machines while knowing exactly what is being done on all machines. Because troubleshooting what happens with your code within the workflow it's important to know what machine it's running on so that you can look at logs and stuff. So essentially, this is what my task for the next year within LinkedIn is going to be, in creating this platform. And that's that. I know I rushed through a lot of the presentation, but I hope you got the gist of it. Thank you.